Hello, my name is Alex Kluwer. In this video I'm going to be discussing the origins of differential impedance. So I will start by using the book that I wrote. I've used this in other videos, but I'm going to be discussing differential impedance from the solutions for a pair of coupled transmission lines. So these are the general solutions for a pair of coupled transmission lines when you have a load impedance, a complex load impedance, and they're both the same. So you can assume that that's the case. We're assuming that they're very similar transmission line circuits. So the load impedance for both lines are the same, and then the source generator and the source impedance for both lines are the same. And what you can do is you're going to be finding the solution for a differential pair. So you know that the input signal is differential mode. And what you can do is define the received signal. So the differential pair will go into a receiver, and that receiver will subtract the voltages on both the lines. So you will define this equation. So this is the received voltage is the difference of these two load lines, like the voltage at the load. And when you do that, you can take all these equations and you'll find this equation. So this equation will give us the received signal for a differential pair. And again, we're assuming that the load impedance for both lines are the same and the source impedance for both lines is the same. And the only thing about the input is that they're differential mode. So basically, if we look at this and we compare it to a single transmission line, we will find that these are very, very similar. And the only difference really is that you have a slightly different propagation time, and you have a reflection coefficient that depends on the differential mode impedance, not the characteristic impedance of the transmission line. And that's the reason that you use the differential mode impedance to impedance match differential pairs rather than the characteristic impedance. So that would be pretty much the only difference, is that you have these two differences. And when you have people who loosely couple the lines, the differential mode impedance and the common mode impedance, which if you were putting a common mode signal in the differential pair instead of a differential mode signal, then you would have to match the common mode impedance to the load and source impedance for it to be impedance matched and for no reflections to occur. And when you very loosely couple, the common mode impedance and the differential mode impedance go to the same, like they go to the characteristic impedance. So when you loosely couple, you pretty much get the characteristic mode impedance, differential mode impedance, and the common mode impedance to be pretty much the same. So you have these equations, it'll be the same. So you have on line where the differential mode impedance is 2 times the characteristic impedance for a loosely coupled case. So when I say differential mode impedance, I mean that the differential mode impedance for a single line. So if you were to look at the required impedance for that line for it to be matched. And that is pretty much it.